Hello students, today we are going to discuss the remaining instructions of 8086 which we have not yet covered in the arithmetic instruction set, that is AAA, AAS, AAM, AAD, DAA and DAS. As like before, first we will discuss the basics of all these instructions and then we will go through the instructions one by one. So let's begin. Starting with the first point, that what is a BCD number. So you must be aware of BCD stands for binary coded decimal. Now decimal numbers range from 0 to 9 and the BCD number is an equivalent binary form of the decimal number. So which ranges from 000, which corresponds to decimal number 0, and this moves on till 1001, which corresponds to the decimal number 9. Thus, BCD values are decimal integers encoded in binary form with one decimal digit per nibble. Okay, so you must be aware of that 1 byte corresponds to 8 bits and 1 nibble corresponds to 4 bits. Therefore, 1 byte equals to 2 nibbles. So this is the first basic concept which we should keep in mind, and the next is what is the difference between a packed BCD and unpacked BCD. When one decimal digit is stored using 4 bits or 1 nibble, it is called as packed BCD. So I can write when one decimal number or one decimal digit is stored using 4 bits, that is also called as 1 nibble, then it is called as packed BCD. If one decimal digit is stored using 8 bits or 1 byte, it is called as unpacked BCD. Let us take an example. Suppose we are having a number 28D. So D stands for decimal. The 28D in terms of packed BCD, what would be its representation? So in packed BCD, it can be represented as, so 2 is represented as 0010 and 8 as 1000. Whereas in the case of unpacked BCD, the same 28 will be represented as 0000 zeros, 00010, that is your 2. So 1 byte occupies 1 decimal digit, so 1 extra, 0010, and the 8 will be represented as 00040 zeros followed by 1000. So as you can see, the unpacked BCD takes twice the number of bits as compared to your packed BCD. Coming to the third point, ASCII values of decimal numbers. So for this, let me go to this chart. This is one website, ASCII code table. The link of this website will be shared in the description. So if you come here on this side, the right hand most side, you see the numbers, that is the symbol, that is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. These have an ASCII values of 48, 49, 50, so on to 57. Okay, so let me tabulate it again. So decimal number 0 to 9 is represented as ASCII values 48 to 57. Okay, so I can write 48 to 57. Now this is the ASCII values for decimal. So when we key in from our keyboard any number like 0, 1, 2, 3, they will get converted into equivalent ASCII format and get stored. But when it is getting stored in the memory, it is getting stored in hex value. So storage is done in ASCII equivalent of hex form. Okay, so what is a hex form? Let us see that. So 48 hex is 30 and the 9 hex is 39 and so on. So if you see the decimal number 5, its equivalent hexadecimal value is 35. you see the decimal number 8, its hexadecimal equivalent in ASCII is 38. So I can write the storage is done in ASCII equivalent of hex, which numbers ranges from 30 to 39. So 0 is represented as 30 in ASCII hex and 9 is represented as 39 in ASCII hex. Okay, so this is your point number 3. The point number 4 which we have to look into is the auxiliary carry flag, that is ACF, which is represented in your flag register, or in some of the registers it will be written as AUXF. So both the things means auxiliary carry flag. The one L is extra. Okay, so auxiliary carry flag. Now what is the purpose of this auxiliary carry flag? So we are aware that the auxiliary carry flag ACF is set to 1 when there is a carry generated from lower nibble to higher nibble. Fine. So this concept you are aware of, so I am not going into these details. What is the lower nibble carry generated to a higher nibble? So this you should be very much well aware while discussing your flag register. So these 4 concepts, that is what is the BCD number, what is the difference between a packed BCD and unpacked BCD, what are the ASCII values of decimal numbers as well as its hex equivalent, and what is the role of auxiliary carry flag. So all these 4 key concepts will be used in understanding your ASCII adjust addition, ASCII adjust subtraction, and so on, along with your decimal adjust equivalent, that is DAA and DAS. Okay, so now let's start with our instructions one by one. The first instruction is AAA, which stands for ASCII adjust after addition. This instruction converts the result of an ASCII addition to unpacked decimal digits. Okay, so please keep in mind, it converts an ASCII addition to unpacked decimal digits. Let us understand this by means of an example. So as you can see in this layout, you are having a keyboard, a numeric keyboard, which has numbers from 1 to 9 and 4 arithmetic operators, and there is a microprocessor in which there are registers, and there is a display which will show what you have typed in. Okay, so you know that if you key in 1, the number which will get stored in the microprocessor will be an equivalent of your ASCII in hexadecimal value. So suppose if an operator, or suppose if you key in a number 5, okay, so it will, suppose it gets stored in your AL register, it will be stored in ASCII equivalent of hexadecimal. So the ASCII value of 5 is 53, and when it is converted into hexadecimal it is 35. So it is very easy to remember. So ASCII equivalent of 5 is 35, 6 is 36, 7 is 37, and so on, and 9 is 39. Okay, so in AL it gets stored as 35H. Fine. Now if you want to add 2 numbers, let the second number be 2. So 32H is the equivalent in hexadecimal form. So when the microprocessor performs addition, so you can write instruction here, add AL comma BL. Now what it will do is, it will add the contents of AL plus BL and it will store it into AL register. So AL plus BL, if you add it, the result will be 67H. Okay. Now when this 67H has to be displayed on the monitor, this should not appear as 67. Okay, this has to be getting converted to 7H. So this needs to get converted to 7, okay, or 7D. Now how is this done? This is done by means of AAA instruction. So let us understand by converting each of them into binary, and then we'll try to understand the algorithm for this AAA instruction. So again I am repeating, when an operator keys the number through a keyboard, it gets stored in the ASCII equivalent of hexadecimal. Okay, and the addition is also done in hexadecimal, but when it needs to get displayed on the display or the monitor, it has to be converted into the equivalent decimal format. Okay, so this is what is your AAA instruction, which is used to display the things in the decimal values. I can write 35H in binary equivalent as 0011 and 0101. Okay, 32H 0011 and 0010. So if we try to add both of them, we get this is 1 1 and you'll get 1 here followed by 0. So let me just do the arrangement. Okay, and here you will be getting 0 1 1 0. Okay, so this is how your addition, that is 35 plus 32 is 67. So this is 110 for 6 and 011 for 7. But when this thing needs to get displayed onto your display monitor, this should be converted to 0 and this number should remain as it is, because if you see ASCII addition to unpacked decimal digit. Now you are aware that unpacked decimal means what? When one byte contains one digit. So one byte will contain one digit, so 7 should not occupy 4 bits but it should occupy 8 bits. So what happens is, first when your AAA is applied or A is executed, this instruction will first check what is the lower nibble content. If the lower nibble is a valid decimal digit, so if the lower nibble is valid decimal, then it will no affect to the lower nibble. Instead, the upper nibble is cleared. So what happens here is 0110 0111 gets converted to 000, and that is 4 zeros followed by 0111. So this results into 07. Okay, and this is the number which gets displayed onto your monitor. So 5 plus 2 is 7, and that is how it is getting displayed. So this is one example. Let us go through another example. Let us consider we need to add two numbers, that is 5 and 7. So when we key in 5, it will be stored in ASCII. So what is the conversion? So 5 you have to add with 30, that is 35H. That is suppose getting stored into A register, and in the B register we have to insert 7. So 7 ASCII conversion in hexadecimal format is 37H. So BL is 37H. So what can we do is, let me convert both of them into equivalent binary format. So 0011 0101 and 37 is 0011 0111. Okay, so now with this thing, if we perform addition, that is add AL comma BL, what is the value getting stored? So if you perform the addition, you will get 0110 and 1100. So this is equivalent of 6CH. Now when after this addition, if AAA instruction, that is ASCII adjust after addition, is executed, so what happens is, first this instruction will check whether the lower nibble is a valid decimal digit or not. Okay, so in this case this is not a valid decimal digit. Okay, so the valid decimal is from 0 to 9, but here it is C. So what will be done here is, to the lower nibble, okay, so to the lower nibble 6 will be added, and in the upper nibble, that is the higher nibble will be cleared, as what we have done in the previous example, because it converts a packed decimal digits into an unpacked decimal digit. So one digit should occupy 8 bits. So higher nibble is cleared. So let us see what happens now. So the higher nibble becomes all 4 zeros, and this is 1100. So if you add plus 6 to this, so plus 6 is 110, we get, so we add 0 plus 0 will give us 0, 0 and 1 will give us 1, 1 plus 1 will give 1 0, so 0 comes here and 1 goes to this part, 1 plus 1 will give 0 here again. Let me realign it. Yeah, now this one, that carry which has been generated from the lower nibble, that is from this part, will not get carry forward to the higher nibble. Why? Because understand, the ASCII addition to unpacked decimal digit. So to have an unpacked decimal digit, the carry which is generated in the lower nibble will go to the another byte and not nibble. Okay, so this will remain the lower nibble, the lower byte will remain as it is, and instead the higher byte will gain that carry. So what is the higher byte in this case? If this content is getting stored in AL, the higher byte is AH register. So AH register will get incremented by 1. So whatever be the content of AH, that will be incremented by 1. Usually what we do is, before starting the addition, the content of AH register is made 0. So this will result in the content of AH register to become 01H, whereas the content of AL register will be 02H. So this 0 will be carried forward like this. So I can simply state the content of AL equals to 02H. So that is what I have represented here. So if I combine totally, AX content is the combination of AH and AL, which is 01, 02H. Right? Now let us have a look at this result. If you see, after AAA instruction, the content is stored as unpacked decimal digit. So this means 02 is basically a digit 2 and 01 is basically a digit 1. So the final answer is 12. If you see here, 37H gives a 5 plus 7 equals to 12, and that is what we have obtained by using AAA instruction. This is not possible if we just finish our result by using add AL comma BL, because add AL comma BL will give you 6C. After we have performed AAA, the final answer is getting converted into your actual decimal values, which is 12. Alright, now we will go to another example to gain more clarity on this instruction. So in this example, let us add two numbers. So one is 9 and another is 7. So the 9, if we convert into ASCII hex value, so we will be getting 39H, and another number, that is 7, if we again convert this into ASCII hexadecimal value, we get content of BL as 37H. So let us try to add this number. Before that, let me convert this into binary. So 0011, 1001, and 37 is getting converted to 0011 and 0111. Right? Now, if we add this, you will get 1 plus 1 is 01, and again 1 here, it will get added to 1, will be again yield 0, so which will again get carried forward to the third place 1, and again it will yield 0. This will again get carried forward to the fourth place, again it will 1 plus 1 is 0, and this will get carried forward. So the final addition, if you do, you will be getting this format: 0 1 1 1 and 0 0 0 0. Alright, so this is equivalent to 70H. Now, after this addition, that is add AL comma BL, we find that the content which is stored in AL register is 70H. If after this we have applied or executed AAA instruction, what happens? Now, this AAA instruction will check the lower nibble. Now, lower nibble should be a valid decimal digit. So if you see here, this is a valid decimal digit, that is 0. Okay, so it's a valid decimal digit, so not an issue. So it will clear the higher nibble. So the higher nibble will get cleared. So if you see the higher nibble gets cleared, it will become 00H. So this is the content of your AAL register. But the answer is not right. 9 plus 7. Okay, so 9 plus 7 should give us 60, and our answer is 0. So there is some issue here. Now, along with the checking of the lower nibble, what the AAA instruction does is it also checks the content of auxiliary carry flag. Okay, so if your auxiliary carry flag ACF is equals to 1, then again it will add 6 to the lower nibble and it will increment your content of AH by 1. Okay, so let us see what happens here. So the lower nibble is 0 0 0. Okay, so 0 1 1 1, 0 0 0 0, it will add 6 to this, so 0 1 1 0. So what do we get here? We get 0 1 1 1 and 0 1 1 0. Fine. Now why here an auxiliary carry flag is set to 1? So if you see here, a carry is getting transferred while the case of addition. During addition itself, this 1 will give a carry to this, and 1 plus 1 will give 0, and again a carry is sent on to the higher neighbor. So this will set your auxiliary carry flag to 1. Since auxiliary carry flag is set to 1, your lower neighbor is added with 6, which will result in 0 1 1 1, 0 1 1 0. Again, the same format, the higher neighbor is cleared, so this will result in zeros. So finally, you are getting an answer 06H. Now this is the content of your air. Apart from this, again the same process will be applied. The content of AH will get incremented, so AH will become AH plus 1. Usually AH is 0 before doing any instructions or any addition like this, so AH will become 1. So let me write the final answer. The content of your AX register will become 0106H. So if you see, it is 01 is basically 1 and 06 is basically 6. Why? Because it is representing unpacked decimal digit, so which is 16, and here again you are getting 9 plus 7 equals to 16. So I hope you have understood the AAA instruction by means of these three examples. Now we will proceed towards understanding the algorithm. From all these examples, what we have understood, we can frame an algorithm like this. So AAA instruction will check if AL equals, or the lower nibble of AL is greater than 9. Okay, so it can be 10 11 12 13 14 15, which has an equivalent hexadecimal of A B C D E F. Okay, or your auxiliary carry flag is equals to 1, then the AL lower nibble equals to AL lower nibble plus 6 and AL higher nibble is resetted or it is cleared. Okay, so it is cleared. Apart from that, the content of AH equals to AH plus 1. Else AL higher nibble is just cleared, and the remaining part of your AL, that is the lower nibble, remain as it is. So this completes your AAA instructions. You can use this algorithm and try to relate the three examples which we have discussed. So now we'll be moving to the next instruction, which is ASCII adjust after subtraction, given by AAS. The procedure in this case is similar to AAA, that is AAA instruction, except that instead of adding 6 to the lower nibble, here there is a subtraction of 6. So let us discuss one example. Suppose the content of AL is 5, which is represented as 35H, and again the content of BL is 2, so it becomes 32H. So if we subtract that, so AL content becomes 0011, 0101, and BL content is represented as 0011, 0010. So if the two of them are subtracted, we get 0000 and 0011. So if you see the case, the answer is 03H. Now this algorithm remains the same. So if you see here, first it will check whether the lower nibble is a valid decimal digit or not. So in this case it's a valid decimal digit, which is 3, so nothing will be done. The higher nibble is automatically cleared, so it will be 0, and the lower nibble will remain as it is, that is 3. So if you subtract 5 minus 2, you will get 3. So this is one example. Let us move to the another example. Suppose you are subtracting 2 from 8, so the content of AL will be 32H and the content of BL will be 38H. Fine. So again let me represent in decimal binary value. So 0011 0010, 0011, and this is 1 followed by 30. So if you subtract this, what do we get? So you can perform the subtraction by yourself. Let us start from the LSB. So 0 subtracted from 0 will give you 0. Then 1 will give 1 subtracted from 0 will give again 1. 0 0 will give you 0. And this 0 minus 1, now it needs to take a carry. This will give you 1 0 and it will result in 1 0 again. So let me just finally do the subtraction. So it will give you 1 1 1 1 and 1 0 1 0. Now see here, while subtraction is being performed, your carry flag will act as a borrow flag. So here in this case, your carry flag will be set. Okay, and that is why you are having here all 4 ones here and 1 0 1 0. So if we convert this, what do we get? We get FAH. Now when AAS instruction or AAS instruction is executed after your subtraction, it will again follow the same algorithm. So it will check whether the lower neighbor is a valid decimal digit or not. So in this case it is A, which is not a valid decimal digit. So it will first clear the higher neighbor and then subtract. So please note, in the previous case we were adding plus 6. In this case we will be subtracting 6 from the lower neighbor. So let me just write it again. So 0 0 0 0, that is the higher neighbor is cleared, and 1 0 1 0. Okay, so if you subtract 6 from this, so 0 1 1 0, what do we get? Let us try to figure this out. So when you subtract, that is 1 0 1 0 and 0 1 1 0, so that is 10 minus 6. If you subtract, you will be getting 4. So here it will be 0 0 0 0 and this will become 0 1 0 0. Now in the previous case, or in the AAA instruction, when a 6 was getting added, the content of AH was added by 1. Or so the content of AH, if it was initially 0, so if you add 1 to that, it will become 1. In this case you will be subtracting, that is the content of AH equals to content of AH minus 1. So if initially it will be 0, then if you subtract 0 minus 1, you will be getting FF or F. Okay, so because that will result in a carry flag to be 1 and it will result in all ones. So let me just highlight here. So initially AH content was 0, so now AH content becomes FFH, and the content of air here, as you can see, is 04H. Now if you, I can just demonstrate this by a calculator also. So let's have a look. So here we have a calculator, so you can use your Windows calculator. So if I go into programmer mode, so you have to select a programmer mode from here, go into hex and you do 0 minus 1. Okay, so 0 was the initial content of your AH, and if you subtract 1, what do you get? You get all F's. Now if you see, if you count the number of F's here, there are 16 in number. Now each digit, that is each F, represent 4 bits. So you can very well guess that my system is a 64-bit system. Okay, you can explore this calculator more. You can see here there are arithmetic shift, logical shift, rotate, circular shift, rotate through, carry, circular shift. So all these things which we have already discussed in your 8086 instruction, you can very well explore all these things in by your Windows calculator. So now coming back to the topic. So here the content of AH is FFH and your content of AL is 0FH. Now what does this FFH means? FFH means here is that it is a signed number and it basically represents negative value. Okay, so it is basically representing negative value. So if we write the content of AX in total, it is FF04H, which means minus 4. So if you see here, 32 minus 38, that is you are subtracting 2 minus 8, because the decimal equivalent of 32 is 2 and the decimal equivalent of 38 is 8. So 2 minus 8 should yield minus 6, but here we are getting minus 4. So why there is a mismatch? Please understand that when we are talking about binary digits or binary numbers, we know the negative values are stored as 2's complement, whereas in the case of decimal numbers, it can be represented as, or the negative values are stored as 10's complement. So this 4 here is now a decimal value. Now if it is -4, so if you take a tens complement of -4, you will be getting as -6. So if tens complement is, you have to do 10 minus 4, you'll be getting 6. So 32 minus 38 or 2 minus 8 will result in -6, which satisfies the value. So here it's the, I can write this -4 is basically tens complement of -6. Right? So this is how your AAS instruction, that is ASCII adjust after subtraction, works. Now let us move to the next instruction, which is AAM, or ASCII adjust after multiplication. Now this instruction converts the product which is present in your AL register into unpacked BCD format. So please note it down. So the product which is there in AL register, this is converted to, or I can write converted to BCD format. Okay, so BCD format, here again I am saying unpacked, right? So the end result is in the form of unpacked BCD format or unpacked decimal. Now this instruction follows a multiplication instruction that multiplies two unpacked BCD operands, that is higher nibble should be 0, and the end result is available in your AX register. So the point to be noted here is the two operands are unpacked BCD operands, and the third point is the final result is present in your AX register. So these are the 3 points pertaining to AAM instruction. First point is the product which is already there in AL is converted to BCD format, and the two operands which are provided by me to the multiplication instruction is unpacked BCD operands, and the final result is stored in AX register. This is done after your AAM instruction is executed, whereas for the other two cases, this is for your mul instruction. Let us understand one example so that things will become much more clear. Suppose we take the content of AL equals to, suppose we have to multiply 5 into 8. So 5, if we convert this into ASCII, it will become 35H, and the content of your BL, that is the second operand, is 8. So ASCII conversion, if you take, it becomes 38H. Now if you see here, the product which is AL is converted to BCD format, unpacked, fine, and the two operands are unpacked BCD operands. So for the mul instruction, that is when we are giving MUL, AL, BL, we should ensure that the two operands AL and BL are unpacked BCD operands. So how will we convert the content of AL and BL to unpacked? So AL and BL should contain only 5 and 8H. So this you can very well do by masking. Now how will you do by masking? You can use a logical operator. So I can use ANI, or sorry, not ANI, AND and operation. So AL comma 0FH. So if I do and AL comma 0FH, this will result in the content of AL to be 05H. Likewise, you can do with BL. Fine. So when we multiply 5 with 8, the end result which is stored in AL should be 5 into 8, that is 40, but this 40 is in decimal format. Okay, so please note the end result, that is 40, is in decimal, so it has to get converted to hexadecimal, because what we are using right now is mul instruction. So mul will give you the end result in hexadecimal format, so hexadecimal format will give you 28H. Now 28 is, as you can convert, this is 40D. So AL basically contains 28H. Now after this mul instruction, we will be executing your AAM instruction. So what happens when your AAM instruction is to be executed? This AAM instruction will provide the final result, okay, in unpacked BCD format in the AX register. So unpacked BCD format, what will it do is it will convert this 28 into decimal. So 28 into decimal, so your AL register content of AL now will become 40D, okay, or in hexadecimal if I write, it will be 40H, because all the register contain hexadecimal value, that is why it is 40H, but here it is basically 28 is getting converted to decimal, so it is 40D. So to avoid confusion, let me just write 40, okay. So AL contains 40. Now this has to get converted to unpacked BCD format, okay. So unpacked BCD format. So what happens here, let us see. If I want to convert this into unpacked BCD format, I should ensure that my AH contains 04 and content of AL is 00. So the content of AX will be 0400. Okay, so 04 represents 4 in your decimal and 00 represents 0 in decimal, that is 40. So 5 into 8 is 40. So what will be its algorithm? Now the algorithm for your AAM instruction is, first convert the content of AL into decimal, then we have to divide the content of AL by 10. So when you divide the content of AL by 10, the content of AH register is basically your quotient and the content of your AL register is your remainder, right? So this is your algorithm. So let me realign it. Yeah. So this is your algorithm for your AAM instruction. Now let us move to the next instruction, which is your AAD. As you can see, the instruction AAD, which stands for ASCII adjust before division. Now I've written here before in capital because if you see the previous instructions, it was ASCII adjust after addition, after subtraction, or after multiplication. But in the case of division, it is before division. So just for example, let me just tell you. So if we are performing mul AL comma BL, we were performing here AAM. Likewise, if we were performing suppose AAD AL comma BL, after that we were writing AAA. But in the case of AAD, first we are performing AAD and then we are performing div. Okay, so div AL comma BL or whatever be the operands. So let us try to understand what this instruction does. AAD instruction converts two unpacked BCD digits in AL and AH to the equivalent hexadecimal in AL. Okay, so I can just write a note here. It converts two unpacked BCD digits in AL and AH registers to equivalent hexadecimal number. Hexadecimal number in AL. So let us understand this by an example. Okay, so suppose the content of AX register is 48. Okay, so the content which is stored in AX register is 48. Suppose we want to divide 48 by 4. So 48 has to be in unpacked format. So see here, it converts to unpacked BCD digits. So 48 will be stored in unpacked format. So how it will be stored? It will be stored as 04 and 08H. Okay, then if we have to divide this by 4, the dividend should be present in your DA register, which I am providing it as 04. Okay, 04H. So again you will be thinking that how 04, 08 and 04 has come. So the same concept which we have used in your AAM instruction. So when operator keys in 4, it will be stored as 34 and then it will be stored 8 as 38. So the masking has to be done of the higher nibble. So this will result in 04 and 08. So how will you mask? The same, you have to use your logical operations, that is your AND operation. Okay, so try figuring it out. I have just showed one example before. And the DL, again, it will be initially 34, but then again due to masking it will become 04H. Now when the division has to be done, this 0408 has to be first converted into a proper hexadecimal value. Okay, this is done by your AAD instruction. That is why this instruction is executed before your actual division instruction. So first it will be your AAD instruction, and then it will be DIV AX comma DL. So what happens with AAD instruction? Let us try to understand. Now AAD instruction will convert two unpacked BCD digits in your AL and AH registers, okay, to equivalent hexadecimal number in AL. So if you see 04 and 08 are two unpacked BCD digits in AL and AH, and this has to be converted into equivalent hexadecimal value in AL. So if you try to calculate the equivalent hexadecimal of 48, you will be getting as 30. So this is 30H. Now DL is already, you are having the content of DL register as 04H, sorry, 04H. So if I now write div AX comma DL, so by uses of AAD instruction you have got AL as 30H. Now after this div AX comma DL is performed. Okay, so now AX is 30H or 0030H and DL is 04H. So what do we get? We know that after the div instruction is performed, the quotient is stored in your, this contains your quotient, and your remainder is contained in your DX register. So this contains your remainder. So the content of AX I can write will be 0000C H. Now why 0000 because if you divide 48 by 4, so you'll be getting 12. 12 in hexadecimal is C. Okay, and likewise the remainder in this case will be 0, so the content of DX will be 0000H. Now I have provided an algorithm for your AAA instruction and AAM instruction. Now it is your task to provide the algorithm for AAS and AAD instructions and mail the same to me. Okay, so this is your task to be done. Till now we have discussed 4 instructions which are ASCII adjust instruction. So the 4 instructions which we have discussed till now are AAA, AAS, AAD and AAM. So all these are ASCII adjust instructions, and these instructions are related to unpacked BCD arithmetic operations. Okay, so these are related to unpacked BCD arithmetic operations. Now we'll be moving to next set of instructions which are related to packed BCD arithmetic. So these are your DAA and DAS. These are related to your packed BCD arithmetic. So let us see how both of them differ with each other, and we'll go through some examples. Starting with DAA instruction, which stands for Decimal Adjust Accumulator. Now this instruction is used to convert the result of the addition of two packed BCD numbers to a valid BCD number. So let me just put it in points. So it converts the result of the addition of two packed BCD numbers to a valid BCD number. Now the result has to be stored only in AL. So please note the result is stored only in AL register. So let us understand this by an example. So let me put it point wise, point number 1 and point number 2. So let us see one example in which the content of AL register is 47H and the content of DL register is 45H. So please note, now we are not taking into account your ASCII values, they are just BCD values. So 4 is another one BCD value, 7 is another BCD value. Likewise, here 4 is again another BCD value, and 5 is another BCD value. So here no ASCII conversion is happening. Okay, so you're not getting the input from the outside, that is your output device, or sorry, input device like your keyboard, but it is your internal calculations which is happening inside your microprocessor. And the intention of this instruction DAA is that even though the calculations are happening inside, the output should be getting displayed to your output device or a display monitor. So that is why even though the calculations are happening in hexadecimal values, the output should be displayed in a BCD or your decimal values. So how is that going to happen? That we'll try to understand using your DAA instruction. So if we take 47 and 45, so if we add this 7 plus 5, you get C, and that will result into carry, and 4 plus 4 will give you 8. So this is 8CH. 7 plus 5 is 12, so 12 gets converted into hexadecimal, that is C, and 4 plus 4 is 8. So 8CH is your final answer, which is getting stored into your AL register. Okay. Now, what this DAA will do is it will convert the addition of two packed BCD numbers. So here we have two packed BCD numbers, that is your 47 and 45, and this it gets converted to your valid BCD number. So let us see here. 8C is not a valid BCD number because you know that the BCD number ranges from 0 to 9. So here if you see 8 is your higher nibble, C is your lower nibble. So in this case C is, which is the lower nibble, is not a valid number. So what needs to get done? You have to add plus 6. So whenever you have to convert a hexadecimal to decimal, you will be adding 6 to this. So what do we get? So 8C plus 6 will result in 2. C plus 6 is 2 and resulting in a carry 1. So which will go to the higher nibble, that is 8 plus 1 will result 9, and this will be 2. So 92 is your final answer. So this 92 is basically your decimal, or I can say your BCD value. So if we add 47 and 45 in decimal, we get the value 92, which is your answer. Okay, let us take another example where the content of AL is 67H and the content of DL is 51H. So if we add these two numbers, so 67 plus 51, this will give, so 7 plus 1 will yield 8 and 6 plus 5 will yield B. Okay, so we get B8H. Now this is the result of add AL comma DL. After this we have to execute the instruction DAA. Now DAA will convert the result of the addition of two packed BCD numbers. So here the addition of two packed BCD numbers are 67 and 51, and it will convert to what? A valid BCD number. So here the number is B8. We need to check whether it is valid or not. If it is invalid, it will convert into a valid one. So let us start with the lower nibble. The lower nibble is 8, which is a valid BCD number. So because BCD number varies from 0 to 9. Now the higher nibble is B. Okay, so this B is not a valid BCD number. To convert this into valid BCD number, we need to add 6. So in total, what we'll do is we will add 6 to the higher nibble and keep 0 for the lower nibble. So we will be adding plus 60H. Okay, so we will add 60H in the case when the higher nibble is an invalid BCD number. So what do we get? So 8 plus 0 will result into 8, and B plus 6. So B plus 6 is equivalent to hexadecimal 1 1. So if you want, you can use a calculator. You can see, go to the hexadecimal, and B plus 6 will give you hexadecimal 1 1. Right? So this one will appear here, and the additional one, because this is the content which we are talking about your AL register. So AL register can only occupy or can hold 8 bits, which is already being used by 1 and 8. Now the additional one which is getting generated will be moving on to your carry flag. Okay, so your carry flag will hold 1. So let me just have a summary of the entire execution. So your carry flag is set to 1. Your content of your AL register is 18H. Okay. Now if we add 67 and 51 in case of decimal, so 67 plus 51 in decimal gives you 118. Okay, this is what we get. This one is equivalent to this one of your most significant digit, and the remaining 18 is the content which is already there in your AL. So this pretty much sums your decimal adjust accumulator. Now let us move on to your next instruction, which is DAS, or decimal adjust after subtraction. This instruction converts the result of subtraction of two packed BCD numbers to a valid BCD number. So as you can see, this is very much similar to your DAA instruction, which converts subtraction of two packed BCD numbers to a valid BCD number. Okay, and the second important point to be remembered here is the subtraction has to be only in AL register. Okay, so let us see one example. Suppose the content of AL register is 67H, content of DL register is 45H. Okay, now 67 minus 45, if we do, so this will give you 22H. So this instruction DAS is executed after subtraction. So first the instruction will be SUB AL comma DL, and after that DAS. So when DAS is executed, it will check whether it is a subtraction of two packed BCD numbers. So it is a two packed BCD number 67 and 45, and whether the end result is a valid BCD number or not. Okay, so here the end result is 22. Now this is a valid BCD number or not, so let us check nibble by nibble. So the first nibble, that is the lower nibble, is 2, which is a valid BCD number, and the other one, that is the higher nibble, is also a valid BCD number 22. So there will not be any change, and therefore the content of AL will remain as it is of 22H. Okay, so which when displayed on your screen or on the monitor will be 22D, which is same as what you would expect in the decimal. So suppose decimal conversion of 67 minus 45 gives you 22D. So this is same. So therefore no change will be observed here. Now let us go to the another example and see what happens. Moving to the next example, let us consider the content of AL to be 45H and the content of DL to be 18H. And let us subtract this and find what happens. So 45 minus 18, observe here. So 5 minus 8, it cannot be subtracted, so one carry will be taken. So 15 minus 8 in hexadecimal will result into D, and 4 will be left with 3, so 3 minus 1, 2. So 2DH is the content of AL register. Now after this subtraction, that is sub AL comma DL, your DAS instruction will be executed. So DAS instruction will check whether the end result is a valid BCD number or not. So if you see this 2D, let us go by nibble. So the lower nibble is D, which is not a valid BCD number. So what we have seen in your DAA, in the DAA, if it is not a valid BCD number, we have to add 6. In the case of DAS, if it is not a valid BCD number, we have to subtract 6. So let us subtract 6. So if you subtract D minus 6, you will be getting 7. Okay, and 2 will be as it is. So 27 is the final answer, which is stored in your AL register. Now let us convert this into decimal, or let us check the decimal equivalent. So 45 minus 18, if it is considered to be decimal, so 45 minus 18 will result 27D, and that is what we have got the answer. So I hope by both these examples you will be able to understand the functioning of your decimal adjust after subtraction, that is your DAS instructions. As we are done going through the entire 8086 instruction set, let me highlight few important ones from examination point of view. In the case of data transfer instruction, the XLAT instruction is important. Then you can have programming based question based on push F, pop F, LAHF and SAHF, and LEA, LDS and LES. They are important from definition point of view also. So now moving to your next part, that is your arithmetic instructions. So in the case of arithmetic instructions, Today we have discussed all the ASCII adjust as well as decimal adjusts. So these set of instructions are very important. Fine. Then IML instruction is important. And what is the difference between IML and MUL and this neg instruction? Okay. So what does neg do? So we have discussed all these things in brief as well as by means of various examples. So depending upon the marks, you can explain them. All right. So CMP instruction is important with respect to 8085 also. Okay. So what is the difference between CMP instruction and sub instruction? So you can get questions something like this also. Coming to the logical instructions. So in the logical instruction, the various shift and the rotate instructions. So we have seen the bitwise movements of all these instructions. So this is very important here. So comparison between your SHL and SHR, as well as why SHL and SAL are similar to each other or why they are same, and how the different rotate instructions work. So you have to show by means of bit movements as we have discussed. Okay. And in this, as a standard instruction, test is very important. Okay. So what is the difference between an AND instruction and a test instruction? So that is also one of the very important questions. Now moving to your next. So in the string manipulation instruction, you will be getting mostly programming based questions as we have discussed. Okay. And depending upon that, you can use either of these instructions. So we have done an ample number of problems related to your string manipulation. Kindly go through each one of them. In the control transfer instructions, so we have unconditional branch and conditional branch instructions. So in this, IRET is important. Okay. And we have understood the different types of call and jump instructions. Okay. So near call, far call, then absolute jump, short jump. So all those things are important with respect to your control transfer instructions. In the conditional branch instructions, mostly what you will be using for your programming will be jump if 0 or jump if equal, then jump if parity can be asked. Okay. And apart from that, you will be having your loop z and loop e. Okay. So loop not 0 or loop not equal. So these two instructions are also important. Moving to your flag manipulation and processor control instructions. So here the flag manipulation instructions are quite simple. So again, most of them will be used for your programming purpose, whereas your processor control instructions, that is this set, I would suggest that all of them are important. Okay. And we have discussed in detail what is the importance of each of these instructions. So all these instructions are quite important from examination point of view. In the next video, what we'll be doing is we'll be discussing few 8086 assembly language programming questions. This will help you in understanding how these instructions are used while programming.